So we can see that our rectangle is 4 tiles wide and 6 tiles long. So we can certainly count the number of tiles, but we also see that there are 4 rows of 6, or 4 times 6, which is 24. We also could see that there are 6 columns of 4, which also provides 24 tiles. So Owen will need 24 tiles. For your homework, your teacher was just awarded $1,000 to spend on materials for your classroom. She asked all 20 of her students in class to help her decide how to spend the money. Think about which supplies will benefit the class the most. So within the classroom supplies discussion board, there is a Excel spreadsheet of the different supplies and how much they cost. So that's where you're going to grab this information from. What you're going to do is write down the different items you would choose for your classroom and how many of each you would choose. Then find the cost of each item. Find the total for each category that you chose from. The different categories include supplies, books and maps, puzzles and games, and then special items. So category that up. Then create a bar graph to represent how you would spend the money from your choices in Part A. Scale the vertical axis by $100. Write all of the labels on your bar graph. Part D. What was the total cost of all of your choices? Did you have any money left over? If so, how much? Scan and upload your responses to the classroom supplies discussion post. Then respond to 2 classmates' posts to answer the following. How much more or less did you choose to spend on each category than your classmate? And how much more or less did you choose to spend in total than your classmate? So respond to those 2 questions on 2 different classmates. Division can be interpreted differently and can be confusing. So we're going to show pictures or diagrams to help us explain the story better so that our understanding is deepened. So here are 2 different divisions representing 2 different ways to divide, and then we're going to show some pictures about each one. Maria cuts 12 feet of ribbon into 3 equal pieces so she can share it with her 2 sisters. How long is each piece? And then Maria has 12 feet of ribbon and wants to wrap some gifts. Each gift needs 3 feet of ribbon. How many gifts can she wrap using the ribbon? Using tape diagrams can help us. So the first question is asking how long is each piece? So this is a how many in each group type of division problem. So 3 times how many is 12? 3 groups of what is 12 is what we're thinking. So we have our tape diagram. All together we have 12, and we need 3 of how many to get to 12? So I can see that there are 4 in each one. So 4 plus 4 plus 4 gives me 12. So each sister will get 4 feet of ribbon. Therefore, 12 divided by 3 is 4. So 12 put into 3 groups is 4. All right, so the second question is asking us how long is each piece, since each gift needs 3 feet of ribbon, so how many gifts can we wrap using the ribbon? So we want to know how many of each group. Okay, so, number lines, I apologize. Refrain everything I just said. We're going to use number lines instead of a tape diagram. So still the same problem, just using a number line. So we have the number line to 12. We're thinking 3 groups of how many is 12. So how many do we need to hop each time in order to get to 12? That would be 4. So 4, 8, 12. We're hopping 4 each time. Now the second question using a tape diagram. The second question is asking how many pieces does one get, or how many groups do we need? So how many groups of 3 is 12? So this time we know that each subset is 3 in our tape diagram, and we know we need to get to 12. So how many 3's can we break this into? Well, we can do 4 of them. So 12 divided by 3 is 4. Therefore, Maria can wrap 4 gifts. Now using a number line. We need to hop 3 each time. So our hops are 3, but how many hops do we need to make? 3, 6, 9, 12. We need to hop 4 times in order to get to 12. Your homework. Scenario 1. John and Luke are trying to figure out which number could be placed in the blank space to make this equation true. John insists that 12 is the only number that will make this equation true. Luke insists that 3 is the only number that will make this equation true. Do you agree with John or Luke? Scenario 2. Becky says that the product of two even factors can be odd. Brandon says the product will always be even. Do you agree with Becky or Brandon? Scenario 3. Louis says that if he partitions a rectangle with an area of 24 centimeters into 4 equal parts, each part will have an area of 12 centimeters. Gwen thinks the area of each part will be 6 centimeters. Do you agree with Louis or Gwen? In each scenario, tell me who is right, and tell me why. Draw a picture or diagram to support the person you choose. Then scan and upload your work to the Who is Right Dropbox. True or false statements. So I've got a list of them here, and we're going to talk through each one if they're true or if they are false. So 4 groups of 5, does that give us 20? True. Is 34 equal to 7 groups of 5? False. 34 does not equal what it should be, 35. 3 times 6, is that equal to 9 times 2? Well, 3 times 6 is 18, and 9 times 2 is 18, so this is certainly true. 5 times 8 is 40, and 10 times 4 is also 40. Notice in this particular one, as well as the previous one, that if I take 5 and double it, I get 10, and if I take 8 and halve it, I get 4. So I'm having one and doubling the other, and still getting the exact same solution. That's also true with the one above. So, not the one above, excuse me. How about 6 times 9 and 5 times 10? 6 times 9 is 54, and 5 groups of 10 is 50. False. This one, similarly, students may be trying to do the addition strategy, where if I subtract 1 from a number and add 1 to another number, it still adds to be the same, but notice that it only works if we're halving or doubling in multiplication. All right, so 2 times 3 times 4, is that equal to 8 times 3? Well, 3 times 4 gives us 12, times 2, or doubling it, is 24, and 8 times 3 is 24. So this is true. Notice that on this one, I could take 2 times 4 and get 8. So that's just the commutative property here and decomposing numbers and rearranging them. 8 times 6, is that equal to 7 times 6 plus 6? True. The right side is 7 groups of 6 plus another group of 6. So I actually have 8 groups of 6 on the right, even though it's not written that way. And then the final one, 10 plus 2 is 12 times 4. Is that the same as 40 plus 2? False. This does not follow the distributive property of 4 times 10 plus 4 times 2. So the distributive property being 4 times 10, and then distributing 4 times the 2 as well. Joey had 120 stamps. First, he gave his sister half of the stamps, and then he used 3 to mail letters. How many stamps does Joey have left? We know that when we have halves, there are 2 equal parts. When we have thirds, there are 3 equal parts. So although third graders don't have a grasp on fractions yet and the rules of fractions, we know the halves, thirds, and quarters and what those represent. So if we have 2 equal parts and using a bar diagram, we have 120 stamps altogether. Then splitting that into 2 equal parts, we'd have 60 on one side and 60 on the other. We know that we give half of our stamps away, so we need to ignore half of them, leaving us with 60 stamps left. Of the 60 we have left, we used 3 of them for letters. So how many plus 3 gives us 60? Counting backwards by 3, we can identify that Joey has 57 stamps left. Homework. Print the attached table of the products of the whole numbers 1 through 6 located in the multiplication pattern drop box. Then color all of the even products in the table. Doesn't matter what color you choose. Sometimes there are even numbers next to each other in the table. However, there are never odd numbers next to each other. Why is this true? Imagine the same kind of table that shows all the products of multiplying two numbers between 1 and 9. Would this still be true? Why or why not? Scan and upload your work back in the appropriate Dropbox. As a reminder for your hint, the definition of an odd number from 2nd grade is a number plus itself plus 1. All right, numbers and operations in base 10. So this is a small little standard that we need to cover. So let's start here with some leatherback sea turtles. When thinking about leatherback sea turtles, what could these numbers possibly mean in this context? The number 4,200, 540 to 1540, 50 to 166, 48 to 96, and 2 to 3. So before I even went any further, I just threw out some meanings, and these are possible meanings. These are just certainly not the correct meanings necessarily, just what first popped into my mind when I'm thinking about sea turtles and what I know about sea turtles. So the top number could possibly mean the largest weight. The second number there could be an average weight. The third one, years of life. The second from the bottom, possible days to hatch and number of eggs they lay. Just some ideas, so conversation starters, if you will. So adult leatherback sea turtles, an average weight of 550 to 1,540 pounds. There is a study tracking leatherback turtles' weight about 800 pounds. What will the new range of turtles weights be for this group? So we have an average weight, and then we have weights of the ones that they've been tracking. How many different possible weights are there? Explain why your numbers make sense. So let's think about how we can show the weights and the number of turtles. Perhaps we can use a number line and place value chart to help us. So I have a number line from 500 to 1,500. I know that the average sea turtles weigh 550 to 1,540, so I put those dots on the number line. The number in question we're thinking about is 800, so slightly more towards the smaller end. So I've kind of zoomed in on 800 here with a new number line. And I'm particularly interested in the numbers between 750 and 840. So the least possible weight is 750. The greatest possible weight is 849 pounds based on rounding. So our possible weights will start from 750, 751, 752, 753, etc., all the way through 849. So we have a large range that could possibly be from. Rounding is an estimation strategy that uses place value benchmarks. So when I think about the number 784 and we want to round to the nearest hundreds, looking at it in its hundreds chart would be appropriate. So I look at 784 and I've got it placed here on a number line so we can see the number. Notice that 784 is much closer to 800 than it is to 700. And notice when I'm rounding, the range in which we would round to 800 is located in pink there. Numbers rounded to a greater place value benchmark are easier to work with. So rounding to hundreds is easier than rounding to tens. And I've got here a list of them. Look at all the ones that we would round to 800 versus rounding to tens, their step through. So there's many more options when we're rounding to the tens place versus rounding to the hundreds place. And another visual diagram, notice the hump there, we reach the 5 mark and we go one way or the other.